I would like to introduce Dean Mas Kabe. He has been with the college in a variety of capacities for over 45 years. He has been Dean of the College of Science and Engineering since 2018. Prior to that, he was our Associate Dean for Research and Planning. And from 1990 until 2005, he was department head for the Department of Electrical and Computer Engineering. So we are so grateful for his service to the college, and he will definitely go down in history as one of the poster children for CSE. So thank you, Mas, for everything that you have done and continue to do for CSE. Mas, as I said, has been with the college since 1975. So Mas, from here, I will turn things over to you and we'll let you take it from here. Thank you.
Well, thank you very much, Megan. You're always kind. Thank you, everybody, for joining us again for another one of these special events where we highlight one of our departments and one or two of our outstanding faculty in this that have their home in the particular department being featured. And of course, today we're tremendously proud and delighted to be able to have mechanical engineering featured. It's really hard to believe that it's been about over a year that we went into a Zoom mode, so to speak. First and foremost, I wish you the very best, and I hope you're all doing well, and I hope that you have been managing to work through the challenges that the pandemic have created for all of us, and that you're on your way. Either you have had your vaccines or you're on your way to moving back to the next stage as we see the light at the end of this particular tunnel. For the college and the university, as you very well know, I don't have to tell you, we've been operating remotely since last March. So it's been certainly a learning experience, not just to say the least. We've had our challenges, but really an opportunity, as you know, for us to learn new ways of doing things, new ways of actually improving some of the delivery of our courses, and even some of our laboratories that are, some are remote and some are hybrid. So one sometimes is forced to look at things differently, and we just had to take advantage of this crisis in a sense to learn to do things better. And so as we look forward to hopefully being back on campus fully next fall, assuming everything progresses as planned, we're expecting that we will be doing things better than we used to do. Again, having the experience and the learning and the creativity and innovations that have taken place during this year. Our students, faculty, and staff, of course, have shown their resilience, ingenuity, and creativity during this whole process, and I couldn't be more grateful for everything that they have continued to do to deliver on our mission. And more so, your support, our alumni, our friends, supporters of the college and the university have really had our backs. You have supported us in so many different ways, and certainly financially, but also in advocacy and spiritually, so to speak, to keep us going, to support our students, our programs. So tremendously grateful for everything that you have done, you continue to do, and for your interest in joining us for a program like this. As Megan mentioned, this is the last one of the Lunch and Learns. As you can see, I'm sort of standing in front of Walter Library. I wish we could have been there as we used to get together, enjoy some lunch together, but unfortunately we can't still this year, but very much looking forward to the possibility of being together again next year. Let me just wrap up with a couple of important areas of priority and initiatives within the college, some of that you may be familiar with, but your continued advocacy for these and support are incredibly important for us. As you know, we have a tremendous demand for our programs from our students, and we've been trying to do our best to create the infrastructure and the situation for our students to get the best education they can get. And one of those is, of course, learning chemistry. And you can't learn chemistry without having an up-to-date and modern laboratory to learn your chemical experiments in there. And of course, chemistry serves students not only in our college, but across the whole university. And if you do remember, if you went through school here, you may remember the old labs that you had your beginning chemistry laboratories in, and unfortunately, things haven't changed. Things haven't changed actually for many, many, many decades, perhaps a century in that respect. So we have had a plan to have a major capital project devoted to changing essentially Fraser Hall, which is behind Walter Library on the river, to a new chemistry teaching laboratory building. And we have a request with the state legislature to get bonding approved for that building. The legislature last year approved design bond funding for the building, and we've done the design, so we're ready to go, break ground. So that's one of our initiatives, which we hope your support and advocacy will help with. The other one is, and some of you may fondly remember Lind Hall. Lind Hall, as of next fall, will be only College of Science and Engineering. Up until now, the Department of English has occupied part of Lind Hall, and we have not been able to renovate that building for much needed space within the College of Science and Engineering. And we're almost there. Again, thanks to the financial support by a number of donors, as well as the funds that the college has been designating to supporting essentially paying for a loan, an internal loan to make the Lind Hall renovation complete. So our plans, we've done the plans, and our hope is actually to begin our construction project for that building project next summer. So just mention these two for your benefit. But today it's about mechanical engineering. So let me begin by introducing my distinguished colleague, the head of the Department of Mechanical Engineering, Professor Susan Mantell, to you. Sue is the James Ryan Professor and, of course, the head of the Department of Mechanical Engineering. She's a tremendous colleague, and I'm absolutely delighted and honored to be serving within the leadership of the college with her. Sue's degrees, all of her degrees are from a little-known school on the West Coast. I think it's called Stanford. Yeah, that's what it is. Right, so Sue received her degrees from Stanford University and has been at the University of Minnesota since then. Her current research focuses on applications of polymers and polymer composites for engineering structures. Professor Mantell is the recipient of a number of Best Paper Awards from the American Society of Mechanical Engineering and has received the National Science Foundation Young Investigator Award, as well as several teaching awards from the students through the nominations of the students, as well as a university level Morse Alumni Distinguished Teaching Professor of Mechanical Engineering. So Sue, thank you again for your service, for everything that you have and continue to do for the College of Science and Engineering and Mechanical Engineering. And I'll hand the mic to you, so to speak.
Thank you, Moss. I really appreciate the kind introduction. And it has been my pleasure to be here for my entire academic career at the University of Minnesota. And really and truly, you know, I started here as an assistant professor, and to get to be the head of the Department of Mechanical Engineering has been a real honor for me and a real privilege. So with that, I'd like to just take this opportunity, first of all, to thank all of you for joining. It's fun for me to see in the chat, oh, my phone is ringing. I'm actually here at work and I still get phone calls in the office. So unfortunately, I didn't figure out to mute that phone, so I apologize. At any rate, it's really great to see so many people here and to see in the chat that you come from near and far. And that is one of the things that we see in the pandemic that I think will stay with us, this ability to connect with people even when they're not in Minnesota. And I think even when people are in Minnesota, having the opportunity to participate without having to drive and get parking is really maybe something that will stay with us for a long time. So here I just want to share a few slides about what's happening in mechanical engineering and really focusing on the research side. Moss mentioned about the labs. We actually have all of our labs have some remote options for our students, and also so from the teaching side, and also some in person, and we have a mixture. So it's been quite a good experience for our students, and many aspects of those remote labs might stay with us as we go forward. But here on the research side, one of the things that the way we like to think about mechanical engineering now is about where we have impact. So yes, we're still doing fluid mechanics and heat transfer and engines and all of that, but just to give you a sense of a few of our impact areas, and here we've grouped them into 5. And then from that, after I describe those, I'm happy to introduce our speaker for today. But here I'll take this opportunity. So energy transition is one of our areas, and it's interesting now. I've noticed the term energy transition is appearing more and more in the news, and it's this idea of how do we move forward to create more energy efficient options and address societal challenges. So here we have people working on solar energy, wind and wave energy, energy storage, and electrification. And as you know, we have a very strong presence in St. Anthony Falls Lab. The director of St. Anthony Falls Lab is an ME faculty, Leanne Shen, and a number of our faculty are affiliated with that lab. In fact, Sung Young, who will be speaking later, is now part of the St. Anthony Falls Lab as well. And I hope many of you know and have had a chance to see Eolos, which is our own University of Minnesota wind turbine in Rosemount. And that has been a great source of experimental data for my colleagues. Another area of impact that we have is environment and sustainability. We have a long history and reputation for outstanding research in aerosols, and that continues. And I think some of you maybe have attended, we had a town hall early on in the pandemic talking about filtration. David Pui, a very well-known faculty member on our department for his research in filtration, but we have newer faculty who also work in the aerosol area. And we do have people who do things that relate to clean water and for just our own lakes, but also in other countries that are developing nations too. So, and then another impact area, of course, for all ME departments, I would say robotics and mobility. The University of Minnesota has a special robotics institute where ME plays a big role. We have people doing research on soft robotics. Here, the image shows something about digging in the soil, but it's the same technology they are applying to very, very small scale cleaning out your arteries. So both the large scale digging in the soil, but also similar kinds of techniques at the small scale, a big grant funded through the National Science Foundation. And of course, we have others who work on muscle-powered walking. There's energy efficient vehicles. These kinds of things are areas that we work in. I just picked a few select projects for this short time. Human health, again, big impact area for mechanical engineering, but also the University of Minnesota. As all of you know, we are in an ideal location to work on human health challenges and problems. And again, ME department is closely affiliated with the Bakken Medical Device Center. Here, I'm just showing an example. I think that's Art Erdman with the glasses on doing medical devices in virtual reality. And also, I hope most of you know that the college and the medical school together through John Bischoff, one of our faculty members, has received funding for an engineering research center in the area of cryopreservation and ATP bio. So again, that builds on some of the expertise in mechanical engineering with freezing cells and thawing them to enable organ transplants and all sorts of other really interesting applications. And then, of course, we have also another area of impact, which is the next generation manufacturing. We have experts in plasma technologies, and plasmas are used for all sorts of things, making chips, but also solar cells. And I think many of you are also familiar with our expertise in 3D printing. We have a faculty member, Mike McAlpine, who does 3D printing of materials that can both be structural, but then he can integrate electronic materials into that structure to create bionic organs. So again, we have these areas of impact in ME, and I hope that you please just check out our website. It's organized around these impact areas, and you can find out all sorts of really interesting projects. I've just picked a few to highlight. And now, Sung-Young, if you want to share your slide, and I would like to introduce my colleague and friend and collaborator, Professor Sung-Young Lee. She is an assistant professor, but soon, it's a little bit premature. It doesn't become official until July when the provost or the regents approve, but she will be associate professor very soon. She completed her PhD and MS in mechanical engineering at another one of those schools you might not have heard of, Massachusetts Institute of Technology, and her BS in ME at the University of California, Berkeley. She had a postdoc at École Polytechnique in France and was an assistant professor in the Department of Mechanical Engineering at Texas A&M until 2017, when she joined our faculty. Conveniently, we had her join in the summer of 2017, which was probably helped her get acclimated, let's say. I think she probably had some winters while at MIT. Her area, as you can see in this slide, her area of expertise is fluid mechanics. And one of the things that she specializes in is reducing complex physical phenomena in ways that we can study them through visualization. So you'll see a lot of really interesting videos and slow motion captions of very common everyday things that you observe. And she solves them with some basic mathematical modeling. So creates new paradigms for looking at fluid mechanics. And I'd like to just give you a little insight. So if you review her CV, or if you looked at her list of talk titles and publications, there's some very interesting ones. Freshwater snail feeding, lubrication-based particle collection on the water surface. How snails walk on water is a small miracle. Crawling beneath the free surface, water snail locomotion. And here's one I think that will appeal to the, well, I guess it's not all fishermen, but dynamic criteria of plankton jumping out of water. So her work brings to light the fluid dynamics behind phenomena we see every day and in nature. So I hope you enjoy her presentation, and I'll look for questions from you in the Q&A that we can ask when she's done. Sung-Young, I will mute myself.
All right. Thank you, Sue. And thank you to everyone who's listening in. I just think there is so many different ways you could be spending this hour, and I'm very flattered and honored that you chose to spend it with us. And hopefully you will be entertained or at least learn something new in the process. I was already also reading in the chat, just to hearing where you're from or where you're tuning in from and your connection to University of Minnesota. And I actually genuinely felt touched. You know, many of you got your degrees many years ago and you're still maintaining this connection to the school and just wanting to hear about what we're doing in the college. I'm very, very excited that you're here. And Sue already went through this really exciting array of research that's going on in the department. And I'm just wondering if I'm the best representation of what's going on in the mechanical engineering department, but hopefully I can add something to the conversation. And also from Sue's introduction, you might be wondering, wow, this person is really obsessed with water snails. So I just wanted to at least show you the video of a water snail, since you already know that I am obsessed. So I didn't mean to include this in the presentation, but here is a video of a water snail that appears to be crawling underneath the air-water interface. So that was my actually PhD thesis from MIT. Who knew you could get a PhD from MIT studying such things, but that's true. You may not think that this is a fluid mechanics problem, but hopefully by the end of this presentation, you'll be convinced that actually it is fluid mechanics problem. And a lot of everyday things that you might observe in nature as well as industry is a fluid mechanics problems. Okay, so I'll get going here. So before I really get started, there's a little housekeeping I want to do. I want to start actually with a little disclaimer, because I assume many of you signed up for or registered for this webinar, having read the title and the abstract for my talk today. But I don't know if you actually made it to the end of my abstract, because at the end of the abstract I mentioned today, I'm going to talk about a little bit about gas migration patterns in soft sediments. But as I was prepping for this presentation, I realized that I think it would make sense for me to stay with a theme or a topic that's more relatable, that you can actually see with your eyes in everyday occurrences. So I actually decided to swap out the last bit of my abstract with by introducing projects that I have going with droplets, because droplet is really something that you can really find in everyday occurrence. So I am sorry if you signed up today because you were excited about gas migration. If you have questions about it, I'll be more than happy to discuss with you. But I just wanted to give you that little disclaimer. Okay, but even way before I get into my actual research, my really main goal today is to maybe hopefully help you fall in love with fluid mechanics, or at least come away with the understanding how common fluid mechanics is. My impression of at least how mechanical engineering undergraduate students feel about fluid mechanics when they first come to my class is that it's a little bit of fear. You know, there is a sense that, oh, fluid mechanics is complicated, it's complex. All of that is true. At the same time, fluid mechanics is literally everywhere, and it is extremely accessible if you choose to look at it that way. So I just wanted to show you how diverse some of these phenomena are. And I also want to convince you that anybody can do experiments in fluid mechanics. All you need is a little bit of imagination and maybe a phone or with a camera and a kitchen sink. So I'll just start with that. So what you're observing, this is literally over a kitchen sink. You have a jet of water coming towards the sink bottom, and you see the water spreading out very uniformly at first, and then there's a jump in the water height. This is called hydraulic jump. The origin of this phenomena really comes down to basically the loss of momentum as the water flows out, and you also have to conserve mass. So it really comes down to all these very simple principles, but this is an experiment you can realize very easily from your own kitchen sink. So there you go. So that's one example of fluid mechanics phenomena that's extremely accessible. But of course, you also know that water isn't the only common fluid, air is as well. So this whole branch of aerodynamics actually falls under fluid mechanics, which is more general, includes both liquids and gases. And I also noticed that there were at least few of you who are actually from aerospace engineering. So you would know that, yes, aerospace engineering is part of fluid mechanics. Here we're just showing you how even when you're designing a vehicle, of course, you do care about how aerodynamic the design is. So that's actually, you have to incorporate the principles of fluid mechanics to make that design happen. So maybe this is an example that everybody already knows. Oh yeah, aerodynamics, that's definitely fluids. But maybe an area where you also might fluids, maybe, although you may not be looking for it, is actually in art. Anything that involves paint, creating patterns using paint is actually using a principle of fluid mechanics, although you may not be thinking it actively. So here I'm just showing you a pottery painting technique called mocha diffusion. Honestly, I don't know where the name comes from, mocha or diffusion, because what you're watching here actually isn't a process of diffusion. It's an instability that's created when a viscous liquid meets another fluid, viscous liquid, which happens to be non-Newtonian. So actually there was a recent study that actually explains scientifically how you can create this beautiful pottery patterns that you see. So even in art, fluid mechanics is there. So since we're basically talking about fluid mechanics everywhere, we can also look up at the sky and notice that clouds, right? I mean, clouds are actually tiny droplets that form. And here I'm just showing you a specific shape of a cloud that's very interesting. And what you're seeing here is an instability, well-known instability fluid mechanics called Kelvin-Helmholtz instability. So when you have shearing of two different fluids types, you might see this type of a swirling pattern, and that's, you can even observe it up in the cloud, which I think is really fascinating. And last but not least, another very common fluid that you might, fluid mechanics phenomena you might encounter is on a rainy day, right? It's kind of hypnotizing, this video. You can sort of ask yourself which drops will stick, which drops will run on the windows. I used to do that a lot as a kid, kind of zoning out, watching the rain, and maybe that's the reason why I'm a fluid mechanician today. But in any case, I'm just showing you there are so many more examples I could have found, but this is just to show you that fluid mechanics is everywhere. Whether it's in art, it's literally in the sky, or it's in your automation, in form of applications, or it's in your kitchen sink. So as you can see, there are so many different directions I want to go, or I could go, but I thought it would make more sense for me to try to stay focused. So let me stick with droplets. So let me imagine just taking this video, which is filmed looking straight onto the window. Just imagine turning it over to the side. So it would look something like this, right? It's not exactly from this video, but just a way to visualize what you think might happen. You basically have a liquid water droplet stuck on a solid surface, and outside of the liquid is, of course, air or a gas phase. So I just wanted to highlight, even in this simple, very simple common phenomena, how much physics is hidden in it. So I just wanted to give you some technical terms that we use in fluid mechanics just to help explain what we see. So actually, I would claim that even in this very simple scenario, the most interesting thing is happening at an interface between solid and liquid. That's where the liquid is touching the solid, and also where the liquid is in touching gas, or that's what we call the fluid-fluid interface. In fact, what's well known is that the fluid-fluid interface experience what we call surface tension. So surface tension is this tensile force that acts along the fluid-fluid interface, and that basically helps form the shape of the drop. So you can sort of help visualize how surface tension might work with this simple illustration. Here you see a water being added to this little penny, so you get a sense of scale. And you see the water doesn't just flow over, although you keep adding the water, because there's this tensile force that helps maintain the shape of the droplet right at the water-air interface. So that's what surface tension force is. So actually, this helps explain how you can have a liquid that can stay suspended on a solid surface despite the weight of the liquid that wants to run down. Because if you actually think about the shape of this interface, and I just told you that surface tension is there's a tensile force that acts along the interface, maybe you can sort of visualize that, oh, the surface tension force helps exert net vertical force that helps stabilize against gravity. So this is why, depending on the liquid size, you can actually have water droplets that stay stuck on the surface rather than running down with gravity. Just one more thing about surface tension is that one more effect the surface tension has, in addition to help to form the shape of the droplet and help it stay suspended against gravity is also, it actually has an impact of increasing the pressure inside the drop. So it's just a little side note I just wanted to say. So the pressure inside the drop is actually larger than the pressure outside, and the pressure difference is actually given by how big or small the droplet is. So that's small snippet of knowledge I might bring back in the later when I actually talk about my research. So that's the thing about surface tension. So right now, all I'm talking about was actually whatever is happening at the fluid-fluid interface. But there's another interface that's of interest here, which is the solid fluid interface. In fact, how much the liquid wets or touches the solid is a very big area of research. And it's because everybody is interested coming up with material that either loves the liquid or wants to avoid liquid. So I just wanted to talk about that a little bit. So this whole area of research that talks about how big is that solid fluid interface, or how much does the liquid or the droplet wet the surface, solid surface, is called wetting, right? That's an everyday term, wetting. And to talk about wetting, I think it's actually a lot more helpful to imagine a droplet on a plane surface, because the vertical surface has too many things going on. So imagine if you just have a horizontal surface and you deposit droplets on it, you can sort of see the angle that the liquid droplet makes with a solid. We call this angle the equilibrium contact angle. I just labeled it theta naught. And the value of this contact angle tells you how wettable or unwettable your surface is. So let's just think about two different extreme limits, because once you see the illustration, hopefully it'll just click. So when the theta naught is approaching 0, that's the limit where the liquid loves the surface. So we call that the hydrophilic surface, right? And when theta naught is approaching 180 degrees, that means the droplet would just beat up and it'll just try to maintain its spherical shape, even when it's touching the surface, because it wants to avoid touching the surface. So that's called the hydrophobic surface. And as you can see, I'm just talking about a simple droplet here, but you will see why this would be such of a great interest to material scientists, because coming up with surfaces that, that love liquid versus really want to avoid liquid is a huge industrial question. When you want to put on your water repellent raincoat, it was rainy yesterday, you want to make sure the material wants to avoid, or material is hydrophobic, because that way you can just, the droplets roll off, as opposed to hydrophilic surface that where the water would just, it would just spread and just wet everywhere. That's something you want to avoid. And it turns out, as an engineer, we learn so much from the nature. So I just want to give you an example of a hydrophobic surface that's directly from nature. So lotus leaf is a great example of a naturally hydrophobic surface. So a lot of what engineers do is actually to study what makes this natural material, lotus leaf, hydrophobic, and they actually try to mimic it in lab by coming up with a synthetic lotus leaf-like material. So I know I'm just going off into a different direction, but what I'm trying to show you is that just by looking at a simple droplet stuck on a solid surface, there are all these different directions you can go. A simple droplet is hiding so much physics and so much room for innovation. And hopefully I also convince you that even though we're starting with a fluid mechanics question about how the droplet acts, it can lead into different disciplines like material science. And it's because fluid mechanics is that common. It's really everywhere. So it's really going to bleed into every other discipline you can think of, because every other discipline oftentimes deal with some sort of a fluid mechanics question embedded in it. And another thing hopefully you saw is that what's interesting about droplet is really happening at the interfaces, whether it's at the solid fluid interface and fluid-fluid interface. And that kind of leads into my research program. So Sue already mentioned that I like to study fluid mechanics, and that's very, very true. And I like to specifically look at different fluid mechanics phenomena. And as you can see, there are a lot of projects, and don't worry, I'm not going to talk about all of them because we'll be here for a long time. They're very diverse, but one thing they do have in common, although it may not be very obvious from this array of videos, is that they all involve a phenomena that happens at a fluid-fluid interface or solid fluid interface, because at the interface is where all these really interesting complex phenomena tend to happen. So today, instead of trying to, talk about different projects, I will try to stay with the theme of droplets. But before I go there, I also want to reiterate maybe what Sue already mentioned in her introduction to my talk, which is that what I'd like to do, the overview of my research program is really to gain fundamental understanding of new physical phenomena that happen in fluid mechanics. And the way we do that is to take something that looks very complicated. It may have a lot of different, competing components to it, but breaking it or reducing it down to something simple. So simplicity is something we actively pursue in our lab. And I think simplicity is underrated. I think a lot of people think, oh, science is complicated because it's complicated. It should be complicated. And you are right, this world is very complicated. Science is complicated. But part of how to conduct science to actually extract real physical phenomena is to break it down into something tractable so we can actually gain real understanding of what's going on. So simplicity is a good thing, at least in our group. That's something we actually really emphasize and work towards. And hopefully you'll get a flavor of that as well. And as Sue mentioned, we like to combine both experiments and mathematical modeling. And just a visual illustration we like to do in our lab. This is a painting by Picasso, a little known artist, who's actually showing the bull, but a different progression of bull from very realistic to something very simplistic, just to show how you can capture the essence of bull, but eliminate things that are just maybe you don't need it there for the sake of simplicity. So this is something we try to do in our lab, although we don't always succeed. Okay, so simplicity is good. Hopefully you got the message. So out of all these different projects that we have going on, I have specifically 3 projects that involve droplets. So what I want to do is just tell you a little bit about how these 3 different droplet projects came about, what application it came from, and how we're actually simplifying it down. And if there's any time left, maybe I'll tell you a little bit more about one of those projects before I wrap it up, because I know your time is important and I don't want to keep you here too much longer. Okay, so I basically told you, I already told you there are 3 projects that I have going on, very, very different, but they all happen to involve water droplets. So I'll just go one by one, introducing where we were inspired to pursue these projects. So the first one involves basically just watching the interaction between droplets and wind. I mean, the interaction between droplets and wind is so common, but turns out this phenomena is central to a number of applications. At least I want to mention 2 of them here. So aircraft icing is basically freezing of formation of ice layer on the aircraft wing, which is very detrimental to the aircraft's performance. A lot of people think of this as a heat transfer problem, but actually this is fundamentally first and foremost a fluid mechanics problem, because when water droplets condense on these wings because it's flying at a very high altitude, you want these droplets to be removed from the surface before it freezes. So really the fact that, so to understand that, we actually have to understand why do some of these droplets remain stuck on the surface even though it's flying at a very high altitude. That means it's always exposed to very, very fast wind. So it really comes down to the interaction of wind and the droplet on a solid surface. And another example of wind and droplet interaction is, of course, in a drying applications. Here you see basically different types of objects that have been wetted by water, and now they're being cleaned off. Or another example of wind and droplet interaction is when you go and wash your hands and, with an air dryer, that's exactly this scenario, right? You want to remove water droplets from your hand. So it comes down to the interaction between wind and water droplets. So these are although these applications look very different, that's what they're sharing in common, the interaction between water and droplets. So we wanted to isolate the problem. So the type of study that we've been doing is literally looking at a simple droplet sitting on a solid surface and understanding how it reacts to incoming jet of wind. So if there's any time left, I'll talk a little bit more about that today. So that's project number one. And these are the applications that inspire to go into that direction. The second project, actually, the inspiration came from nature. So it turns out when you have a raindrop impacting an infected plant, it actually causes this dispersal of plant pathogens, which is undesirable. So the spread of spores from this infected plant is a well-known phenomenon. And of course, this is of interest to our agricultural community. But this is also fundamentally a fluids problem, because what you have here is a water droplet dropping and impacting a surface that's covered by particles. So here maybe the interest has been, okay, we want to track where the spores actually go, but you can also look at it as a fluid mechanics problem and try to really understand how does a droplet respond when it impacts the surface that's covered by the particles, and also where do the particles end up. So this is another project that I've been working on with my collaborator, Professor Jung at Cornell. So that's project number 2 involving droplets. Again, inspiration is very different, but the process is the same. Take the inspiration, find a way to make it a simple, tractable laboratory type problems that we can solve systematically. So the last of the 3 projects that involve droplets. So this one is also very different. Every one of them is very different. This one involves coalescing filters. So I don't know if anyone is here from the filter industry. So coalescing filters are used to basically separate out water droplets that are dispersed inside the fuel, because water droplets in fuel is something you do not want to have, and it can actually cause damages to your vehicle if you're actually using fuel that has a bunch of water droplets embedded in it. So these filters are actually used to take the water droplets and make the droplets merge with each other or coalesce so they can actually drop out by gravity. So we've been working with Donaldson, the local filtration company here. And here I'm just featuring an experiment that features a sample of their coalescing filter. So I'll just show you. So you see the little water droplets come in and they're basically interacting with each other. Some of them are merging, hopefully growing bigger. So by the time they come out on the other side, hopefully they'll get bigger. Not all of them are, but you'll see. But you should see them growing bigger. That's the idea. The filters are there to coalesce the droplets. But as you can see, this is a very complicated process. The filter is a very complex network of fibers or porous material. And sometimes what we realize is that although they're supposed to coalesce droplets, sometimes they end up with a smaller droplets as well. So what we're trying to do, inspired by this very beautiful and interesting study, is to really take it down to a single pore. So how does a droplet react when it's presented with a single pore? And how do we actually prevent things like breakup, as you saw in this video, which looks really cool, but it's not something you want to see in a filtration process. So again, very, very different application that inspired a very different study, but the theme is the same. These are 3 projects that involve droplets, all different scales, all inspired by different problems. So I actually did prepare, a couple more slides to talk specifically about this one of the projects, the droplet dynamics driven by airflow. But I'm just carefully looking at my time here. So Sue, I don't know if you don't mind jumping in, but I might just start to wrap up. What do you think?
Yes, I think it might be good to wrap up, although could you do maybe just something real short on a little bit behind the airflow droplet, like maybe a 2-minute version?
Yeah, sure. Okay.
Okay.
So yeah, that's a great idea. Okay. So I just show you. So the way that we take something that we conceptualize and take it to the lab is to make it as systematic and repeatable as possible. So you can imagine if you just have a water droplet and you impose a jet of air, it's going to, cause a droplet to break up. And in a scenario like this, when you're just putting an air nozzle on top of it, it's really hard to control the flow. So what we try to do was to actually, instead of looking at a single jet of nozzle like this, we wanted to actually mimic what happens in an air drying application. So we bought an air knife, which was hooked up to the air compressor, so we can actually impose a very well-controlled jet of wind towards our water droplet, and that would create the zone of very high pressure. So this would be a type of experiment that we do, and we just film it from the side with a fast high-speed camera. So these are 2 droplets, same size, but we're imposing wind at 2 different speeds. And you're going to see the one on the left is at lower speed. The water droplets stays together. It's oscillating in place, whereas the water droplet on the right is going to eventually split. So we can see just by changing the wind speed, you are going to get 2 different behaviors of the drop. And this is something we can measure and track depending on the droplet size. And maybe this isn't something you may have expected, or maybe you have, but as you can see with a larger droplet, it actually takes much lower speed to split. And it's all because of surface tension, which I introduced earlier, but I won't go into that right now. And another thing that we observed is that, so again, these are 2 experiments with the same droplet, but slightly smaller at 2 different speeds. So you would actually expect the droplet on the left to split and the droplet on the right to not split or just hang in place because it's small. But another thing that we introduced here is that the droplet on the right is a little bit more off center than the droplet on the left. And because of the difference, we might see something new. So I'll just give it a minute. So droplet on the left actually splits. That's exactly what we would expect. The droplet on the right is not supposed to do anything. It's supposed to hang in place normally. But because we apply the jet off center, we actually see the droplet escaping to one side. So this is what we call depinning. So actually going back to the application that inspired this whole thing, we want to actually encourage droplet depinning. We want droplet to actually escape and get off the surface, whether it's with aircraft icing application or air drying application. So this is something we're studying a lot right now, and just skipping all of that, we actually started to simulate droplet depinning with our new set of simulations, which we're really excited about. And I'm sorry, I just don't have time to go into the details today. But really, I just wanted to end with this. Just going back to the same images that I came up from the start. I think really, I just wanted to mainly say 3 things with my talk, is just for you to realize that really fluid mechanics is everywhere, and it's actually very accessible, and it's highly visual. So anybody with an iPhone could do an experiment right now, recording a new fluid mechanics phenomena. And the second thing I want to say is that droplet is a very complex, although very common, complex object that can actually be important in so many different applications. I hope you saw that today, and it's really governed by surface tension, and it actually inspired different types of disciplines like material science to develop new kind of textures, which is really exciting. The last thing I also want to emphasize, want you to take away from today's talk is simplicity is actually really the key that drives fundamental research. For you to really understand what's going on in every physical phenomena, you have to actually take something complicated and boil it down to something simple. So that's just one last thing I wanted to just emphasize as a takeaway message, and just thank my students and colleagues and collaborators who contribute to my research program. Although I just didn't get a chance to talk about the actual research as much. But I'll just end right there. So thank you so much for sticking around. And if you have any questions, I'll be happy to answer them.
Thank you, Sung Young. It's really quite interesting, and I do find the videos really catches your eye. Now we have a couple of questions, and I thought that might be from somebody, an ME alumni, Jim Colton, who I happen to know is a real photographer. So I am not surprised that he has questions here.
Okay.
So in the Q&A from Jim, in the project of a droplet impacting the plant, did you study how the droplet breaks up?
No, actually, so that particular study, so this study was actually not done by me. It was done by my collaborator, Professor Sunny Jung at Cornell. So the point of this study for them was just to track, hey, where do these spores end up? So they were mainly studying the airflow that's generated by the droplet impact, as well as the transmission or the transfer of the spore. They didn't really study, okay, so what happens to droplet? That's why in our study right now, we're actually studying, okay, how does the droplet behave differently when it's impacting a solid surface without particles versus with particles, because obviously the droplet dynamic changes as well. So this paper, which is beautiful, doesn't talk about droplet dynamics per se, so that's the goal of our current study, is to really study how the droplet itself responds to the presence of particles. Yeah.
So, and I should have grouped the two questions together from Jim, because then the second, which was a follow-on, and I think you might have answered, it's just something about, did you quantify the size of the droplets formed? So in your new study, is this one of the things you're doing then?
Yeah, so in our new study, so that's the nice thing, right? So we're actually using glass particles. So we get to, or synthetic particles, so that includes glass or plastic. So we get to exactly control the size, density, distribution of particles. It's a lot more systematic. So what we found is that size doesn't matter very much, which is interesting, but density matters a lot. Yeah, the density of particles has a high impact. So it turns out the heavier the particles are, it can actually cause the droplets to break up a lot earlier than normally would. So yeah, the effect that we found is really highly non-trivial and not intuitive. So yeah, we're actually excited about that. I get really excited if we find something that's surprising. And we have a model to explain that. So yeah, so there is not so much size dependence, but weight dependence.
Okay, and then one last one from Jim, I guess, which it's, and probably relates to a couple of your topics. Do you ever model the droplet formation? Is that?
So droplet formation,
You know,
so you mean thermodynamically, or?
well, I'm not sure how to interpret that, but you know, you always start with there's a droplet on the surface, right?
That's right. Yeah. So
Right.
because I'm not doing like a phase change, I'm not. So there are definitely people who are studying that. Nucleation problem is a big one, although it's air bubbles mostly. But yeah, I guess, yeah, I'm usually just sticking with, okay, let's just hold the temperature constant. Temperature is not really a parameter. We have a droplet. It's already condensed. What does a droplet do? Although, yeah, there are a lot of people, especially in the thermal side, who are studying how does a droplet form? Why does it form here? How do we prevent that? There'll be more condensation, nucleation part of the study. I'm more in the pure fluids camp where we have a droplet, what do we do with it? Yeah, but that's a great question.
Okay, I do have one that I saw in the chat, but I'll repeat here because time is short. So do you ever envision from Betty Wheeler, do you envision that high airflow might be able to de-ice planes in the future instead of using the polluting fluids? So, you know, that was one of your examples, and we know that, yes, go ahead and say, what do you think?
Yeah, so, but that's the puzzling thing, because if you think about aircraft icing, because aircraft is moving at such a high speed, it is constantly, there is wind all the time, but these droplets are really really good at hanging on to the droplets. So when what it comes down to is, I think people are trying to figure out what kind of material or texture should the aircraft aircraft wings should have, so it can discourage droplets from actually holding onto it. But once the water droplets form or aircraft icing forms, I think, I don't know whether just exposing it to wind itself will be a very effective way of cleaning it, because it's already formed. So I guess what we're trying to show here is maybe there's a way to make sure that the droplets cannot stay on the surface and it would just be driven off even before it can freeze. I think that'll be the best case scenario. But what to do, how to effectively clean the surface when the ice has already formed, I think that's a different question altogether. And I don't know if the wind will be the best way. Hopefully it'll help, but I think to prevent this, I think would really come down to collaborating with the material scientists, actually. Yeah.
Sure. Okay, and I think we are almost at the end, but Jim had one follow-up, which was he meant droplet formation at impact. In 20 seconds or less, do you model droplet formation at impact? So once the impact hits.
Oh, okay. So we are coming up with a model for this problem, the droplet impacting the surface.
And then
So
more droplets forming.
yeah,
after
but
impact,
we don't,
right?
but the model breaks down when the secondary droplet forms, because when the droplet go from 1 to 2, that becomes a singularity. So the simulation tends to break down. So not quite, yeah. But
Okay.
that's a very sharp question, actually. That's the limit of our model, yeah.
So, all right. So Sung-Young, thank you so much for sharing your work, and please feel free to reach out to Sung-Young. You can find her on our webpage if you have more questions or want to know how her work is applied. It's really very much part of our everyday life. So thanks again, Sung-Young, and I'll turn it back over to the Dean's group. Have a great day, everyone.
Thank you, everyone.
That was wonderful. Thank you. I'm sure there would have been a ton more questions, so I'm sorry that we have to cut you off, but as you mentioned, we try to be respectful of time and get everyone back to their days. But I do want to mention that, remind you again that we will share a follow-up email in the coming week or so that has a recording to the session, as well as additional resources, including a list of upcoming events. 2 events that I wanted to point out are our Curiosity Drives Progress lecture series, Giants of Earth and Sky. Or space, actually, excuse me. That lecture is on Wednesday, April 14th, and it will feature 2 of our distinguished professors speaking about solar flares and dinosaurs, and the light that those topics can shed on our day-to-day mysteries that we're trying to solve. The other I wanted to mention is the Ramalingam Memorial Lecture with a keynote speech, Digital Machining Processes. That event is being hosted by the Department of Mechanical Engineering. So perhaps the mechanical engineers in the room per se are familiar with our very beloved professor, and this event is in honor of him. That will be Wednesday, April 21st. And again, links to registration information for these will be shared in that follow-up email. And we always have a full running list of events on cse.umn.edu/college/events. And for those of you who receive our CSE Events Digest, we have one of those going out next Tuesday. And there are, I believe, 11 lovely lectures, poster sessions from across the college and its centers that are coming up between now and about May 5th. So we hope that you are able to join us for some or all of those things. And from here, I'll let Moss say his goodbye.
Thank you again. Thanks very much, everybody. Professor Lee, what an amazing talk. You can see why we're so excited about highlighting our outstanding faculty with these opportunities. So thank you so much again for your support. I do remind you, perhaps you know already, if you don't know, the college, the provost is about to begin the search for the next dean of the College of Science and Engineering. I hope you stay engaged in that process as well as it progresses, and we will look forward to new leadership in the college in the coming months. So thank you so much again for joining us. Thank you for your support. we're truly grateful for what you've done to make the Driven campaign such a success for the university, for the College of Science and Engineering. Much appreciated. Stay well and take care of yourselves.